Thank you everyone for coming to this talk. And I'm excited to share with you all the work that I've done on contact-based perception and planning for robotic manipulation in novel environments. As examples of these novel environments, we consider these homes where each one is a little different from each other and they can change frequently. Occlusions in particular are common in these environments and are a major challenge for visual perception. So in many cases, contact becomes necessary to actually collect more information. Existing approaches to this problem mostly involve sequentially picking and placing objects to remove clutter. While effective, this may not necessarily be the most efficient way to accomplish the task. And one aspect that we think deserves consideration is the contact averseness of traditional planning methods. So compare this to a human behavior when reaching into places that you can't fully see. Instead of being contact averse, we actually actively seek out contacts and rummage around. This is the type of behavior that my research seeks to enable, but it's a very challenging problem. So can we at least get part ways there? To scope the problem down, I only consider tasks where contact is necessary, such as due to limited vision from occlusion, and only consider rigid household objects, such as from the YCB datasets. So here we briefly consider what makes this problem so challenging. First of all, we don't have great robot skin sensors, and to actually perceive a contact, the robot often has to push hard enough to actually move the object. Combined with the local nature of contact information, it becomes unclear how previous observations may become invalidated by each perception. To not go into too much detail, we do contact localization, which is the task of determining the positions on the robot that actually made contact. We use prior work shown here. This thesis will cover 4 parts, and we will progress from considering the challenges of being blind in a static environment to perception in a dynamic environment, and finally to generating rummaging trajectories in a dynamic environment. But before diving into each chapter, I would first like to present some tools that were extensively used throughout. The general theme of my research is dealing with limited perception and the uncertainty that arises because of it. Fully modeling uncertainty and performing inference on that model is typically computationally expensive. Thus, one of my focuses is on making the algorithms as parallelizable as possible. I've created some open source libraries that has become quite popular outside of just our lab. And since they're extensively used in my work, I'll briefly explain each one. So first is a model predictive control library. It implements a batched version of the model predictive path integral control. And the idea is to sample many action trajectories, roll them out using a dynamics model, scoring each trajectory with a cost function, and then combining the trajectories based on their costs. I've additionally implemented a currently unpublished smoothing method by subsampling control and using kernel interpolation for them in between. I've also implemented a differentiable kinematics library that is useful inside dynamics functions where we want to solve the inverse kinematics problems to multiple goals in parallel. We can solve 10,000 solutions in 300 milliseconds. And lastly, I've created a library that supports voxel and sign distance functions, or SDFs, which will be extensively used. An SDF evaluates the sign distance to the surface of an object, and the gradient of it is a smooth approximation to the object surface norm. The library enables parallel lookups of SDF value and gradients across millions of query points. So the first part in the thesis that I'll present is trap-aware MPC. This is a hierarchical controller that detects and escape traps. And in the interest of time, I will only briefly describe what it does while showing results. So traps in general are state cycles, and in the peg and hold task comes from unmodeled walls. The robot is trying to insert the peg into the hole at the other side of the wall, but it cannot actually visually perceive the walls, so it has to make contact with them. And it recognizes that it can't make any more progress due to being blocked by the walls and labels that as a trap. It then continues progressing towards a goal, remembering previous traps to avoid re-entering them. We compare this against some baselines that also reasons about traps, but we see that in many cases, because they don't actually dynamically adjust how they deal with traps, they can actually block themselves out of reaching the goal.
Actually, Johnson, let me just clarifying question. This term traps, just not, I don't know if that's standard or if that's your terminology. Maybe is it related to local minima?
Yeah. So sorry for I omitted some of the math here, but they are attractors under the dynamical system of like the system dynamics given a given MPC or like some kind of controller. So in this case, we have a local controller that's being given to us for the problem. So the idea is that you've tuned the controller on some nominal environment and you want to deploy it on this novel environment. And given this whole system together, traps are attractors or essentially local minimas in this whole system.
Got it. Thanks.
All right. Yeah. So next, we're moving on to environments with an unknown number of movable objects. So we first consider just the perception problem of tracking the position of previously made contact points. And our method here is called soft tracking using contacts, or abbreviated into STUCCO. So how we actually use the contact points for downstream applications is we consider the object retrieval task, or we call it the blind object retrieval task. The idea is that through a sequence of contacts, we track the positions of those contact points. Note that there's an unknown number of objects, and we have to then segment the contact points after being tracked into our estimates of objects that they're associated with, and then perform pose estimation given those segmentations. And then once we have those pose estimates, we perform object retrieval via grasping. So prior work in multiple object tracking is well studied in computer vision, but it is definitely an underexplored area outside of it. Using primarily tactile sensing has only been shown to track a single object, but in signal processing, we see that there are sensor agnostic methods for multi-target tracking that we'll use as a baseline and show that there is underlying assumptions there of having dense information. So our main contribution of STUCCO is a tracking method that works with the type of sparse data that contacts produce. We also show that it is the only method that works consistently across a variety of blind object retrieval tasks.
Johnson, another clarifying question here, because you're sort of saying, being a little bit unclear about the sensor. I'm just trying to really understand. This is a contact sensor, or are you going to be specific about what the specific sensor is? Because just saying sensor dense or sparse is pretty ambiguous.
Mm-hmm. Yeah, so in the real experiment, I will go into detail the actual type of sensors we use. But in this case, the contact localization for this sim experiment is actually done via the contact particle filter. So what the robot can estimate is the applied external wrench. And we are assuming that each contact is only occurring at one contact point. That's why it is sparse.
I see. And you get a wrench at each of those points?
No, we get an applied wrench at the end effector wrist. And then through a contact particle filter, we can actually estimate on the surface of the robot end effector where that contact was likely made.
Okay, good, thanks.
Yeah. So concretely, problem definition, what we're given is a robot trajectory. So this is the pose of the end effector, a sequence of them, and a object dynamics model. So this can be a very simple model, such as assuming sticking contact when in contact, and the object linearly translating with the robot end effector. We'll show in experiments how observation updates can correct for model error in this case. Our goal is to track the position of all contact points made and segment them into corresponding objects. So in the diagram here, the different colored points represent the segmentation of the tracked contact points. And we're going to evaluate the tracking quality with contact error, which is the smallest Euclidean distance from a contact point to any surface, as well as the Folks-Mallows Index, FMI, which evaluates segmentation. So we call our approach soft tracking because we do not explicitly keep track of and propagate contact to object associations. So as depicted here, we don't know if 3 separate contacts were made with one object or 3 separate ones. Instead, we maintain a belief over just the positions of the contact points that we represent with a particle filter, where each particle is the position of all contact points. So next, we'll show how this belief is updated. So at a high level, we start with the trajectory of robot effector poses. Then using prior work, we detect contact as well as localize the contact point on the end effector. So again, here we're assuming only one contact point per contact, but we relax that assumption in our later work. Then we apply our tracking method to estimate the position of all contact points. And this is a sequence of predicting how the previous contact points will move with each new contact, and then evaluating the likelihood of each of those estimates. For downstream tasks, we extract the most likely estimate from our belief, and then segment the points based on distance to find connected components, which we interpret as belonging to different objects. So our prediction model for the update is based on the simple assumptions that points closer together are more likely to have come from the same object. So in the diagram here, we've made contact at time t and observed contact point pt. So we then predict the movement of all the previous contact points by sampling their connection to the new one. So the probability of a connection is based on the distance with a length parameter that we tune on a training set that should have objects of the expected size. We then apply the given dynamics model to the entire connected set. And this update process might be different per particle because we're doing the sampling each time. And for our update process, we evaluate the likelihood of each particle based on the assumption that contact can only occur on the robot surface. So on the diagram to the right, we see an example where P1 was not sampled to move together with the other contact points. The result of this is that the end effector of making the previous contact actually overlaps with this contact point. If the contact point was truly there before, then at the time of the previous contact, the end effector should have actually detected contact with this point as well. So the whole particle actually receives low likelihood as a result. And just to go into more detail about how we're using this in the application of blind object retrieval, this is a task where we're given the action sequence that all the baselines execute. We have a known target object, and we also have no vision of the system. And how this proceeds is that we track the contact points, we segment the contact points into objects, and then we estimate object pose on each one. In this work, we use iterative closest point as the algorithm for doing the pose estimation, or ICP. And then after the action is executed, we perform grasp at where we think the object is. So to briefly introduce the baselines that we'll compare against, they're mostly split into 2 classes. One is the probability hypothesis density filter, or the PhD filter. They also do not use any hard associations between the objects and the contacts, and a family of clustering methods depicted below here. So the idea of these is that we cluster at each step and then apply dynamics to the clustered set of points. And all of these methods are tuned on the same training set that we use for hyperparameter tuning. So here we first take a look at our method on one of these simulated tasks. So the blue box shows the predicted pose, and the maximum likely particle is also shown, basically all the positions of the points, with the color indicating their segmentation. So we see that initially it grouped the points on the box and the can together, but once it actually rummaged in between them, it was able to correct for that previous mistake. Okay. Then we compare our method against some baselines and see how there are common failure modes. So again, the same action sequence was used for all methods. So for the family of clustering methods, we see that they often fail because the initial contacts were ambiguous, and because they only keep one estimate, you can't expect them to actually correct reasonably in hindsight. The PhD filter propagates using linear Gaussian dynamics and are state and control independent. So what this means is that they make global updates that do not actually utilize the locality of the contacts. And what this results in is sometimes forgetting contacts with each action step. So we perform 20 runs of the simulated experiments each, with slight noise added to the action sequence each time. So then we take a look at our method on a real experiment. So here I'll explain how we actually detected the contact points or localized them. We used a combination of the soft bubble and the contact particle filter. So the soft bubble sensor has a depth camera inside that measures deformations that we compare against the deformations readings of it being known in free space. If we also detect a high applied external wrench at the end effector, but do not actually observe anything from the bubbles, then we use the contact particle filter to localize contact on the other parts of the end effector. And here we execute, again, here we're executing actually a fixed action sequence that we found to actually sufficiently localize the object enough times. So one challenge here that we noticed was the difficulty of actually detecting the contact with normally objects of normal mass. Here we actually had to augment the object by loading them down to have sufficient signal to noise ratio. So in terms of results, our method performs the best on all metrics across all blind object retrieval tasks. It was actually the only one that achieved at least 65% grasp success on all of them, and no baseline achieved more than 5% on all the tasks. For the real task, we did not have ground truth, so we only evaluated grasp success. So in summary, what we do is we do not keep track of hard object associations, but instead propagate a belief over the contact positions. This allows us in hindsight to correct for poorly sampled connections. When we estimated the pose using ICP, it took many contacts to actually collect enough information to reliably estimate the pose. Our next work seeks to improve this while also characterizing the pose uncertainty from the limited information. So first of all, how do we have a hope of estimating the pose more efficiently? One thing that we noticed from the ICP is that many of its estimates actually violated free space constraints that we had to process post estimate. So the idea is, can we use the free space directly? And in terms of estimating the uncertainty of the pose, we propose a way to generate a set of diverse and plausible poses. So concretely, for input, we have these observed free space points and observed surface points, and we'd like to produce a set of diverse and plausible pose estimates pictured here that are consistent with the observation. Okay. We also note that in our experiment, segmentation near occlusions were quite unreliable. So we ended up using the vision just for providing free space. And to do so, we can do ray tracing from the camera frame to its measured depth. In terms of related work here, there's been quite many variants of iterative closest point and also many other object registration or pose estimation methods, but we'll focus on a specific few. One is a variant of semantic ICP, where we treat surface and free space as different valued semantics. Another is Stein ICP, which uses Stein variational gradient descent to approximate the distribution of poses from running ICP. We also note that there are many learning methods, for example, learning the occupancy or learning to estimate the pose directly. Compared to these methods, ours can generalize to novel objects and cameras, as well as introducing multiple sensors without any retraining. So in terms of contributions, we produce a method that outputs a set of plausible poses instead of a single estimate. Our method is also a novel application of an algorithm called quality diversity optimization, or QD, and I'll explain later what this does. As well as we notice a large performance increase over baselines on these real and simulated tasks shown. So concretely, how we define the problem is that we're given an object shape, which we can generate an object frame SDF from it. And we're also given a set of observed positions and semantics here. So semantics is a random variable that can take on 3 different values. For example, free space, occupied, or having a known SDF value. For example, if we detect a surface point, then we know that its SDF value is 0. And our problem definition is that we are concerned about the discrepancy between the observation and an object shape. So the idea is to find a pose that actually minimizes this discrepancy. In terms of ground truth, we can actually find a plausible set of poses that are epsilon discrepant away from the ground truth. And we can generate the set by densely enumerating consistent poses. This will take a long time, but we can do this for ground truth. And in terms of how to actually evaluate our estimated set of poses against the ground truth plausible set, we use a prior metric called plausible diversity. And we'll see an intuition of what this means in the next slide. But the D distance here is a distance between transforms, and we use the chamfer distance between transformed objects as the distance. So here we see the ground truth plausible set on the left. In the middle is an estimated set that has bad plausibility because it has elements that are highly unlikely. And on the right, we have a set that has bad coverage because it does not actually cover the plausible set. So our method is called constrained pose hypothesis set elimination, or short for CHSEL. And at the core of it is we formulate a differentiable relaxation of the discrepancy introduced before. So there are some nice properties of this cost, such as it allowing us to use the SDF gradients to actually gradually improve the discrepancy. Additionally, we use this cost inside of quality diversity optimization to enforce diversity while retaining plausibility. So quality diversity optimization is a problem different from usual optimization where we want to find one best solution, but it tries to find the best solution for each given solution feature. And this feature can be, for example, the translation component of a pose estimate. And if we use it as such, then it becomes a problem of finding the best orientation given each translation. We use a variant of QD optimization called CMA Mega, and this method is able to utilize the differentiability of our cost function to accelerate its search. Next, we talk about how we actually pose estimation as a QD problem. So first of all, we use the translation as the feature, and our idea is to limit the quality diversity search over the local minima that we find by running stochastic gradient descent on the discrepancy cost. So visually, we initially start with a set of pose estimates. This is our prior, for example. It can be very random. We then apply stochastic gradient descent on our cost function, the discrepancy, to find out what are the local minima from running essentially ICP plus. From these local minima, we then construct bounds on the feature space to limit our QD optimization to just over the set of local minima. Then we run QD optimization to find what are the actual best local minima. So here we're going to show our method on a real task. This is a probing task where we make a sequence of probes that sometimes makes contact with the objects, but sometimes not. And we want to estimate the plausible poses each time. So note that we're able to use both contacts made with the object as well as the free space that the robot sweeps out. So here in the initial position, the camera is actually occluded by the top of the cabinet so that it can only see parts of the free space. So let's take a look at a comparison of our method against the baselines qualitatively. So ground truth plausible pose is shown in the top left, and our method is shown on the top right. We see that qualitatively, they are actually the closest. Next, we take a look at why some of the baselines might specifically fail. So Stein ICP, or SVGD, Stein Variational Gradient Descent, produces outliers because it's fit to the distribution of ICP results, which includes bad local minima. For the CVO baseline, which is a semantic ICP variant, we noticed that data imbalance was a major issue for it. So we had many times more free space data than surface point contacts. And we found that it actually worked better when just fed these surface points. And lastly, for ICP, it doesn't use free space, so clearly it's not plausible. And quantitatively, we see that our method in blue also does the best. Orange is an ablation of our method that does not use the differentiability of our cost function to actually accelerate the search. We see that it also performs quite well, but we run it for enough iterations that this didn't end up making a difference. So in summary, CHSEL characterizes the pose uncertainty as a set of plausible pose estimates. And we generate these plausible pose estimates using quality diversity optimization on the discrepancy, which is a relaxed measure of constraint violation of the semantics. Next, we move on to our last chapter, which is called rummaging using mutual information, or RUMI. This is a natural extension of our previous method, where we're given the observed data, and here we decide where the robot should go to explore next to best reduce uncertainty. Prior work in this field in active exploration primarily focuses on one step ahead and does not consider robot trajectories. Most also do not manipulate the object, either by relying on vision or assuming that the object is stationary. So most methods that involve learning are also specific to trained objects and camera views. Our advantage in this case is that we can generalize across sensors and known objects without any retraining. So in terms of contributions, we formulate a conditional pose distribution given the observed data big X, which is the information observed at the robot trajectory. And we also describe how to update this posterior. We also formulate an information gain based on the mutual information between the pose and this big X. Additionally, to use inside of an MPC framework, we introduce a stochastic object dynamics model and a reachability cost to prevent the object from being pushed out of the workspace. So concretely, we're given a prior over poses PT, as well as a dynamics that we execute, but we do not actually know, so we can't use this in planning. And the goal is to maximize the mutual information or the expected information gain between the robot trajectory and object pose. This is equal to the mutual information between the semantics at the positions that the trajectory will cover. So that is one detail I'd like to clarify. The random variable here is the categorical random variable of semantics at each position X that a trajectory will sweep out. And this is similar to what we introduced before. We simplified the known SDF value to just be the surface semantics. So there's now 3 classes: free, occupied, and surface. In addition, we assume that we're given a sensor model. So this sensor model provides the probability of observing each semantics given some underlying SDF value at that position. So we note that sensors can detect both false positives and false negative contacts. This is why we need the sensor model. But we notice that our method is actually quite robust to this model, and we didn't have to calibrate it to real data. So we formulate the pose posterior inspired by energy-based methods by fitting a Boltzmann distribution to the discrepancy. Here we're interpreting the discrepancy essentially as an energy. The lowest energy state is at discrepancy equals 0, and that results in the most likely pose estimate. We represent this with a particle filter because it is computationally efficient, and we do not need the full representation power of, for example, a Gaussian process. And under this interpretation, CHSEL from our part 3 can actually be interpreted as sampling from this posterior. Next, we introduce how we actually formulate the information gain. So unfortunately, we cannot deal with the correlation between the information at each semantics at different points. So one thing we do is make the major assumption, that is a caveat commonly made, of independent information gain from each point. This is equivalent to assuming the conditional independence of all these semantic variables given the observed data set. So based on this assumption, we can look at the information gain from a single new point. Unfortunately, this results in a KL divergence where the inner expectation is over a new distribution for each query point. And this becomes intractable to actually evaluate. Instead, we approximate this with the reverse KL divergence. And intuitively, what this results in is that informative points are those that have some semantics value that would invalidate currently likely poses. And substituting in the conditional pose distribution presented before, as well as simplifying and approximating it with pose particles, we end up with this expression, which we can actually evaluate. Okay. Next, we consider how we actually do planning using this mutual information. So first of all, to allow efficient replanning, we voxelize the information gain over the workspace to produce something that looks like the figure produced before. But we notice that greedily optimizing for this information gain often leads to the robot pushing the object out of reach. So we consider explicitly dealing with this by introducing a reachability cost that seeks to keep information within the reachable region. Lastly, we have to plan for object motion. And we observe that information is only gained by relative motion of the robot and the object. If you continue pushing in a straight line on the object, for example, you're not actually gaining any information despite covering this, the area. So we create a stochastic dynamics model that we use to predict the displacement of the object. And this allows us to transform query points into displaced object frame during planning. And we use all of this inside of closed loop KMPPI. Next, I'd like to briefly introduce the baselines that we're comparing against. The first baseline is a Gaussian process-based implicit surface method, or GPIS. And the idea here is that we use a GP where the input is position and the output is a field where 0 represents the object surface and positive values are outside the surface. This is depicted in the top right, where we have a view of a mug with the red line being the 0 level set of the fitted GP. So GP, in the bottom right, we have the variance of the GPIS. And this will be the cost function that we use to actually motivate the exploration. So one non-trivial thing to do is how do we actually encode shape information to the GP? Prior methods have used primitive shapes, but none have explored both unknown pose as well as known shape. In those cases, they actually know the shape as well as the position of the object. So to do so, we augment the input data to the GP with the workspace points that have high free space semantics value. If we don't actually augment the data, then we observe that the GP baseline will explore the corners of the workspace where we don't have any observed free space points. Next, we introduce a simple sliding heuristic inspired by many methods that use sliding as a mechanism for collecting information. And lastly, we consider two ablations where we have no reachability cost and also have no information gain cost to consider the value of each one. We performed experiments over 3 configurations and 3 simulated objects. So we take a closer look at the box experiment, which is a 3D navigation problem searching for the pose in SE3. So what's plotted here is the pose particles. And initially, it's all over the place because we actually start with no visual observation of the object in this case. So the robot has to determine essentially which way the box is facing and also if it's upright or on its side. And to do so, it has to at least visit some corners of the object, which we see it doing here. Okay, and here we have pose particle convergence and it terminated its exploration. So next, we take a look at our method in comparison to all these baselines. And these will be executed quickly, but we can take a look at the executed trajectory afterwards. So we see that the slide baseline fails very quickly because it could not actually physically get around the box and started pushing the same location repeatedly. Reach only failed because it was only concerned about pushing the box closer and didn't disambiguate between the two different poses shown in the top right. And GPVR likely failed here because it had to be fit on heavily downsampled input data to be computationally usable. Next, we show our method on a real experiment on the mug. So here we see that initially most of the information gain is where the handles could be, and we plan a sequence of actions around it that doesn't push the mug out of reach. So the depth camera point cloud is shown with detected surface points in red, with re-estimation of each time using the camera as well. So even without making contact, we can still constrain the pose by observing free space as we see now. Okay, and then after the next contact, we make contact with the handle, and this is enough information for us to collapse the pose estimate. Next, we take a look at how each of these baselines behave in this case. So first, we consider the GPVR baseline. So immediately we can notice that compared to ours, the highest variance is actually behind the handle instead of at the handle. And this is due to the use of the matern kernel, or this is a kernel that is based purely on distance between the points, and it can't distinguish the certainty of observing the back inside of the mug from the uncertainty of the handle. This means that it is not a good enough way to encode known object shape. Next, we consider the sliding baseline. We note that here the mug is quite light, so it's making some mistakes in actually estimating when it actually made contact with the mug. And soon it pushes it out of the way. We see similar behavior if we only greedily consider information gain. It also pushes the mug out of the reachable region because there is no other explicit penalty other than the fact that it can't collect information in the future. So next, next we take a look at the reach-only ablation, which we note that it fails because there are ways to push the information to be in the workspace to be more reachable without actually collecting the information. So we see here that it pushes the information to be in a more reachable region, but it doesn't actively go out to collect this information. So in terms of evaluation, we considered the likelihood of the ground truth pose given our pose particles. This likelihood is only high if the pose estimates is both correct and certain. However, we can't evaluate this without the actual ground truth pose. So we consider an alternative proxy, which is the convergence of the pose particles. And we experimentally note that in simulation, we have high linear correlation between the negative log likelihood of the ground truth pose with the pose particle convergence. We have a 0.87 out of a possible 1. And so this can be evaluated without the ground truth pose, which is why we use this as a termination condition. In terms of results, ours is the only one on the simulation tasks to succeed on all tasks. And we also achieved the best convergence on the real mug task as shown in the figure here. Ours is in blue. And we also considered that our runtime is much faster than the GPIS inference, despite it already being heavily downsampled. So to actually get closer to real rummaging, what we presented is has only been validated on a single object, but to get real rummaging, we have to handle multiple objects and relax our knowledge of the object model. This can potentially leverage my previous work on STUCCO of treating each segmented object as the candidate object and adding all the information gains from each one. But these are all work that I hope to get done in the future. And with that, I would like to conclude this presentation. I'd like to thank my lab mates and collaborators over the years for their ideas and support. And of course, thank you to Dimitri and Nima for your support throughout my PhD. All right.